Swayam Prabha. Digital India. Educated India.
So welcome back. In this lecture we shall be primarily looking at some of the basic functionalities of the operating system. So this is the second lecture of the first module, and as I said, we shall be looking at the basic functionalities of the operating system. What are the principal responsibilities that an operating system has, and a little detail about those things. What are the some of the nitty-gritties and some of the very salient features of those. Let us see. Talking about the basic functions of an operating system, the operating system, the software is designed in the form of several modules. Now, there are a few modules that are part of the operating system. As you can see here, it is called the process management, processor management, memory management, file system management, and of course, overall for all these modules you need to have adequate protection and security, because in your computer system not only a single program is running, but in general a number of different programs are running. So, generally you shall be having some protection and security. So, as I said, here we shall be very briefly look at these 5 modules. These are the main functional modules of an operating system, and what these actually are. What are the main functions of these modules? Okay. Let us start with process management. Now, here we start by introducing a very important concept in operating system, the notion of a process. This we shall be explaining in further detail later again. Process, loosely speaking, is defined as a program in execution. Like you see, when you create a program, you compile it, you generate an executable code. The executable code resides in the disk in the secondary memory, right? But when you start running the program will be loaded from the secondary memory into the main memory, and then the instructions which are there in that program will get executed. The processor will come into the picture, the CPU. Now, this program, when it is in the state of execution, we call it as a process. We shall be seeing exactly what a process is and what is the main differences of a process with respect to a program. We shall be seeing that. But generally speaking, remember one thing, the program which is residing in the secondary memory is treated as a passive entity. Passive entity means a program just consists of a set of instructions, machine language instructions, which if you run will perform certain task. So, in that sense a program is a passive entity, it is just stored in the disk, but unless you are actually running it, nothing will happen, right. It is stored in the disk in a passive state. But when you run a program, a few other things also happen. The program becomes a process, and this process is an active entity, because you see, as I said, when a program is running, the program has to be loaded from the secondary memory into the main memory. Okay. So, the first thing the operating system must do is to allocate enough memory space, enough space in the main memory for the program to be loaded. Once it is loaded, there may be some space required for some additional items like data space and other things. So, when all of those spaces are allocated and the program code is also loaded in memory, then you are ready to run the program. That is referred to as a process. Now, in general, in a computer system, I also mentioned it during the first lecture very briefly, there can be multiple processes in various states of execution. In a computer system, even if there is a single CPU, at the same time there can be multiple programs running, which means there are multiple processes. So, you think of a scenario whenever you are using a computer system, let us say a laptop. Normally what you do? We do some work, we check our emails. In the background, maybe we are playing a song, playing some music, that music is also playing. Maybe we are downloading a large file, that is also going on in the background. So, there are so many things which are going on at the same time, right. So, there is the existence of multiple processes. This we will see later how these are actually handled by the operating system. There can be multiple processes in the system. Obviously, they can be in various states of execution. Some of them may have just started, some of them are in advanced state of execution, just about to finish, and so on. Moreover, talking of a process, a program in execution, there is a concept of a thread. This also we shall be discussing in detail later. The process can be single threaded or multi-threaded. So, right now we are not going into the detail, we are only telling you that for a single threaded process there is a single program counter, which means there is a single thread of execution. The program counter always tell which is the next instruction to execute it, right. So, if there is a single program counter, you have a single thread where the PC continuously points to the next instruction, and in that order the program gets executed. But in general, you can have a multi-threaded version of the process where there can be multiple program counters. There are multiple so called threads, and with every thread there is a separate program counter. So, each of the threads can be in various states of execution, which will be indicated by the program counter, which is the next instruction that particular thread is executing. Well, one simple example of multi-threaded program is, suppose you are using a browser. Well, often we use multiple tabs in the browser. Okay? In the different tabs we browse different websites, we do various other things. So, there are so many things going on together, but browser as a whole is a single process. There are multiple threads and each of the tabs indicate those threads. From some of the threads, maybe I am writing a mail, some other thread I am downloading some file, some other mail I am going to a website and browsing something there, and so on. Okay? Fine. Now, let us try to understand the notion of a process. What I said, suppose I have a secondary memory. This is my secondary memory. Without loss of generality, let us say this is disk. So, when I create a program, the program will be stored in the disk. Let us say in the disk I have a program which is stored. Let us say this program is P1. P1 is a program, right. Now, what I am saying, that when I have a main memory, this is my memory. So, when I want to run this program, okay, let me note it down. P1 is a program, it is a program. Now, in main memory, when I give a command to run the program, what happens is that some space is created. Typically, for a running program, there are several different regions of memory space which gets created. I am following the terminology that is used in the Unix or the Linux operating system. So, there is one section which is called the code section or the text section. The code section is sometimes also referred to as the text section. Then you have data section. then you have a section which is called heap section, and there is another section called the stack. There can be more sections, but these 4 are the most basic. Okay. So, all these taken together, this constitutes the process corresponding to this program P1 when it is loaded in memory. Later on we shall see what are the roles of these different regions, but for now just remember, in the code section the instructions of the program P1 are stored. In the data section, some of the data that are used in the program that will be stored, specifically the global variables, data space for the global variables wherever you are declaring, or the static variable that will be stored in the data space, data section. Now, heap section is a section whose size is not fixed, it can vary with time. So, whenever you allocate space in memory during the execution of a program, for those of you who are familiar with C or C++ programming, you may be knowing that there is a function called malloc. Using that you can dynamically allocate some space. So, those space will be allocated in the heap area, and stack is a data structure which starts with the end and it grows in this direction towards the lower memory address. And whenever you make a function call, whenever you pass parameters to a function, recursion, the stack is heavily used. All the data pertaining to a functional call are saved in a stack, and stack is a last in first out structure. Function calls and returns are also last in first out. So, in a stack we maintain information about such function calls and returns. This is very standard thing, this is implemented in almost all computers. Okay? Fine. Now, talking about the processes and the role of the operating system, the point to note is that the operating system needs to keep track of all the processes that are currently active in the system. So, it is supposed to manage the processes that are running on the system. Specifically, there are several responsibilities of an operating system. For example, whenever you require to create a new process, maybe you are running a new program, or you will see later that there is a facility that a process can create another child process, it can create more processes. So, creation of a new process, that is one of the responsibilities of the operating system. Also, some process after it has completed its execution, you will have to remove it, because every process which when it is running, it is occupying some space in memory, right. So, unnecessarily why it should occupy space? If it is finished, you should release this space, which means you have to remove the process from the system after it has finished execution. And also we shall be seeing later again that the processes which are running, they need not be independent programs. There are cases or instances where the processes may interact among themselves. Like I am citing a very simple example. Suppose you have a bank account, someone is trying to deposit some money into your account and someone is trying to withdraw some money from your account. So, these two entities can be regarded as two processes, and your bank account which is stored somewhere, that is a common space. So, the two processes must communicate among themselves to access that common data. So, there are many ways by which the processes can communicate among themselves. We shall be looking at them. Specifically, we shall be looking at the concept of shared memory. The processes will be sharing some memory, and through that memory they can exchange messages, or there can be explicit message passing. One process can send some message to another, or can receive a message from another, right. And whenever you have such processes which are running together, they are communicating among themselves, synchronizing them becomes a big problem. So, synchronizing such processes which are termed as concurrent processes, because they are logically running at the same time, they are running together. So, there are many problems that arise, again we shall be looking at these things later on. Something like critical section problem, this is very important. How do we ensure that the processes run correctly without some kind of errors? There is something called semaphores which help in solving the critical section problem. Sometimes two or more processes might get stuck during execution. A process is waiting for some other process for something, that some other process is also waiting for some other process for something. So, there can be a cyclic chain like that. This is called a deadlock. So, similarly, handling of deadlock is one of the things the operating system can look at. And when I say that the operating system need to keep track of the processes, so the information about every process is maintained in the form of a data structure, that is called process control block or PCB. Every running process has a separate PCB created for it, and the PCBs are stored in certain way. We shall be talking about these later, and using the PCB we can maintain all information, and also we can manage the processes that are running on the system. Okay. Okay. That is about the processes, the running programs. Now, let us come to another important module of the operating system. This is called processor management. Processor is nothing but the CPU, central processing unit, the hardware where the actual instructions are getting executed, that is the CPU. Okay. Now, you have heard about multi-core or multi-processor system. These have become quite common today. So, nowadays we have computer systems where there are multiple processors available. Okay. So, there can be one or more than one processors in a computer system. Essentially, they are all central processing units, CPUs. So, we mentioned earlier, they can be of the same type or they can be of a different type, symmetrical or asymmetrical. Okay. Now, one of the role of the operating system is, you see, there are multiple processes which are running, all right. Suppose there are 10 processes which are running. It is quite possible that in a computer system there are 3 or 4 CPUs that are available. So, those 10 processes can be sharing the processor time on those 3 or 4 CPUs. Like one process will be running on CPU 1, the second process can be running on CPU 2, third process on CPU 3 and so on. So, in this way multiple processes can be running on the CPUs together in parallel. If there is multiple number of CPUs, then parallelism or parallel processing in true sense is possible. Okay. But if it is not there, if the number of CPUs is less than the number of processes, then what you have to do, often you will have to share the available CPU time among the number of processes. Like what can happen is something like this. Let us say there is one CPU only and there are 10 processes which are trying to run. So, what you can do, we can allocate some small amount of time to each of the processes. Like I say that the first process will be running, let us say, for 5 milliseconds. Then the second process will be running for another 5 milliseconds. Then third process will be running for another 5 milliseconds. So, in that way, in a cyclical fashion, we are giving some CPU time to all the processes. Okay. This is one way we can share the CPU among number of processes. There are other ways also we shall be seeing. Broadly there are two approaches, one is called multi-programming, other is called time sharing. So, the method that I referred to just now, that is called time sharing, cyclically sharing the CPU among the number of processes. But effectively whatever method we use, the main objective typically is to minimize the waiting time with respect to the users. Suppose I am a user, I am sitting on a terminal, I have typed some command, I should get my response back fairly quickly. If I get the response fairly quickly, I will have an illusion that well, I am using the computer system and the computer system is only mine, no one else is using. I am typing, computer is responding. But in reality what is happening, computer is not only responding to my requests, there are other programs also running, it is also sharing its time among them. Okay. So, most of the modern operating systems that we see today, they are based on this time sharing operating system. Sometimes it is also referred to as multitasking. There are a number of tasks which are running in a concurrent fashion as if together. Okay? Fine. Now, talking about this multiple processes running on a CPU. So, what I am saying is that there is, let us say, a single central processing unit. There is a process P1, there is another process P2. Let us conceptually look like this. These two are running program. Now, because there is one CPU, at any given time only one program can be running on the CPU. So, what I say is that let us say P1 is currently running on the CPU. We say that process P1 is currently active and the other process P2 which is also trying to run is currently waiting. So, whenever P1 releases the CPU or the operating system takes processor away from the P1, then it can be allocated to P2. So, then this will be deallocated and P2 will be given the CPU, something like this. So, when a process P1 is running on the CPU, just think in this way. Suppose the process P1 is running, under what condition the operating system can stop P1 and give the processor to P2? Broadly, there are two reasons for this. That means, a process is running, the OS operating system forcibly stops the process, takes away CPU from the process P1 and gives the CPU to some other process, let us say P2. There can be two reasons which are mentioned here. One is that the scenario where I said that the OS is giving equal times to all the processes, let us say 5 milliseconds, 5 milliseconds. So, it can be using a timer. It loads a timer with some value, with every clock the timer is decremented. Whenever it reaches 0, it interrupts the processor. So, whenever a timer interrupt comes, the system will know that the time slice, it is called, the time slice for the previous process has elapsed. Now, I have to move to the next process. So, the first possible reason is a timer interrupt. Timer interrupt arrives means, it means that the current process has exceeded the CPU limit, it must stop and OS can give it to the other one. And the other reason which is mentioned here is that the process itself P1 wants some service from the operating system. For example, it needs to do some input or output operation, it needs to print something or read something from the keyboard or something like that. So, whenever that happens, the IO input output operation is relatively much slower as compared to the processing time. So, what happens is that whenever such a thing happens, P1 will temporarily stop its execution, CPU will be made available and the CPU can be given to the other process P2. Okay? And this request, P1 is requesting for something that I told, this is done through a system call. We shall be again going into some detail on this a little later. And of course, a process can stop and other started whenever a new process arrives into the system. So, CPU also have to be given to the new process. So, there are multiple reasons why a process may need to be stopped and the CPU may need to be given to some other process. Okay? Fine. Next, let us come to memory, which is another very important resource in a computer system. All running programs need memory, operating system needs memory. Okay? So, one of the very important responsibilities of the operating system is to keep track of the available memory. Whenever a process requires some memory, it puts up a request to the OS and the operating system will be allocating memory space wherever it is available. Okay? And we shall be seeing later again in detail that typically memory is divided into small pieces or chunks which are called pages. So, whenever memory is allocated, it is allocated in terms of these pages. Okay? And there are some other things also. Memory space is limited, there can be many processes which are trying to run. If it so happens that the memory becomes full, then some of the processes from the memory may temporarily be moved out to the secondary memory and later on it can again be brought back. This is called swap out and swap in. Swapping a process out of the memory or swapping a process into the memory. Okay? This will be done depending on the memory requirement of the processes. If it finds that the memory space becomes very limited, there are more requests coming from the processes for memory, then some of the processes may need to be swapped out. So, broadly speaking, memory allocation and memory deallocation. Deallocation means when a process has finished execution, whatever memory space it was occupying, it can release this space, okay, so that some other process can now use it. So, let us see these things in a little detail with the help of an example. Let us say I told you, suppose this is my secondary memory disk. My programs are originally stored in disk, let us say. Let us say that I have a program, let us say there is more. Let us say there is a program P1, there is a program P2, there is another program P3. So, I said whenever the programs get loaded into memory, they become processes, because other than the program code, there are something else. Now, let us look into the memory. See, there are many ways operating system can do it. One simple way is, whenever a program requests for some memory, it allocates a block of contiguous memory location and the program or the process is loaded there directly. So, let us say it may so happen that the process P1 gets loaded here, P1 gets loaded here, P2 also requests for some memory, maybe P2 is loaded here, then P3 requests, P3 may be loaded somewhere here. So, this is one approach. So, wherever memory is available, operating system will allocate a chunk of memory, contiguous chunk of memory for the corresponding process or program. So, You see, if it allocates like this, there are some regions which are already allocated, right. This is allocated, this is allocated, this is allocated, but there are some regions of memory in between which are still available. So, if some other process P4 wants to allocate memory, and if it can be allocated in one of those regions, free regions, so operating system should be able to allocate. So, the operating system should be keeping track of both the allocated space in memory and also the available free space in memory. Both these things must be kept track of by the operating system. Okay. And the other one I told you, in most modern day operating systems, this memory allocation is not usually done in chunks. They are done in small units called pages. Like, let us give an example. Same thing, let us say P1, P2, P3 are there. What I can say is that this process P1 is divided, let us say divided into 3 smaller chunks. These are so called pages, 3 pages. Similarly, let us say P2 is divided also in 3 pages, P3 in 4 pages, let us say. Okay. Let us give some names. The first page here, let us call it P11, P12, P13. This one let us call it P22, 21, P22, P23, and this one P31, P32, P33 and P34. These are the actual pages in the program which need to be loaded in memory. Now, in these cases, the memory will look like this, a little different. The memory logically will look like as a space where there is a number of frames. These are called frames, page frames. So, in a page frame we can load a page. There are many such page frames in memory. The idea is that whenever a process is requesting for some space in memory, let us say P11, P12, P13, these 3 pages must be loaded in memory. It is not necessary that they need to be loaded one after the other together. Let us say P11 may be loaded here, P12 may be loaded here, P13 may be loaded here. Similarly, for process 2, P21, P22 and P33, maybe P21 will be loaded here, P22 will be loaded here and P23 will be loaded here. Like this, the pages can be allocated space in memory wherever it is available, and in between, we shall see this in much detail later, there is something called a page table which will be maintaining the mapping, that which page is loaded in exactly which page frame in memory, so that there is no confusion where a page is located. So, roughly speaking, this is what memory management is all about. You need to keep track of the memory, you need to keep track of the occupied space and also free space, and whenever a process requests for some additional memory, operating system must be able to allocate space in memory where it is available, right. Okay. The next important thing concerns the files, file system management. Well, you are all familiar with files and folders. In every computer system, we have the concept of files. We store information in terms of files, document file, text file, PDF file, image file, okay. And we normally organize them in separate directories or folders. Now, a file system is some kind of a structure which is of course stored in secondary memory, where I can store all these files, I can create these folders, subfolders, I can manage these folders, subfolders, I can store the files in a proper way there, and also I should be able to keep track of the free space in the disk, which part of the disk is occupied, which part of the disk is free, and everything, all information about this. So, whenever we have a secondary storage like a disk, as I am saying, that we normally store information on the secondary storage in the form of files. The most common type of storage devices that we see today are of course the disks. Disks are still available on most of the computer systems, and nowadays the SSDs are coming, solid state drives. They are much faster and they have no moving parts. In a disk there is something which is rotating. So, if there is a vibration, there is a chance of the disk getting corrupt or getting bad, but in SSD there is no such problem. And you may not have seen magnetic tapes normally, but in large computer installation, whenever they want to keep data backup, they keep it on magnetic tapes, because a magnetic tape can store huge volumes of data, huge amount of data. So, that is used as a data backup. And in these secondary storage devices, we have the notion of a file system. So, we shall be studying file systems later, how directories, subdirectories are stored, how the files are stored, where the data for the files are stored, and so on. Okay. So, the files are typically stored as part of the file system, and they are organized as directories and subdirectories. Directories and subdirectories are also referred to as folders in some operating systems. They call them as folders. And the operating system allows you to specify some kind of access control on these files and directories. Like for example, I can say that this is a folder that belongs to me, no other user should be able to see the files which are inside it. Now, in Unix, every file, it can be a normal file, it can be a directory file, they are associated with some protection bits, 3 bits. Every file has 3 protection bits, one for user, one for group, and for others. It says user, group, and others, 3 bits. If the user bit is 1, it means that the person who has created the file, that is the user. If it is my file, I have created it, I am the user. The user will be able to access the file, and users are usually created, when the user accounts are created, there is a notion of a group. For example, in a class there are some students, all students belong to a group. So, if I want that the file I create can be accessed by all members of the group to which I belong, then I will set the group bit also to 1. And if I want that anyone can access the file, others, then the other bit also I will set to 1. So, depending on what I want, I can set some of the bits to 1, some of the bits to 0. So, if I set it as 1 0 0, it means only myself as the creator, as the user, will be able to access the file, no one else will be able to use them, right. And as I have said that in a file system, it also keeps track of the data blocks where the actual data for the file are stored on the disk. Okay. So, this we shall be studying later in more detail, do not worry. And with respect to the operating system, for a file system there are certain useful utilities or functionalities that are supported. Firstly is mounting a file system or unmounting a file system. See, mounting, I am just briefly trying to explain what is mounting. You see, normally on a computer system, sometimes we insert a folder, we insert a pen drive or an external hard disk. Suppose we put in a USB pen drive to a USB port. After some time, what we see? We see that the pen drive gets mounted. Mounted where? There will be a folder in which that name of that pen drive, whatever name is there, will be shown, which means I am mounting my file system on that pen drive at that point on my existing file system. My existing file system was something, there are some files, folders. When I insert the pen drive, that file system gets attached to that existing file system. That means I am mounting a new file system to some point in an existing file system. And afterwards, when I am done, when I eject that pen drive, it unmounts, it is removed from that point. So, mounting and unmounting, that is one important thing. And of course, creating a new file, deleting a file or deleting a directory, creating a directory, all these functionalities will be supported. And I talked about access permissions, users, groups and others. So, there are instructions, there are commands to change the such access permissions of the files, and means everyone cannot do it. Suppose you are the owner of the file, you can do whatever change you want, right. So, change access permissions of the files and directories, and of course, when you are actually using a file, you are opening it, you are reading it, you are writing some data into a file, closing a file, this kind of things should be supported by the operating system. So, these are some of the functionalities of a file system that are supported by the operating system. Okay. Now, the last part is protection and security. See, operating system need to provide a number of security mechanism to the users, primarily because in a computer system I am not the only person using it. There are other programs which are also running on the computer system, and when I am connected to the internet, I really do not know what other programs are running. Okay. So, I must be very much sure about my program, my data, it must remain secure. Whenever my program is running, there are other programs also running together. Okay. So, when my program is loaded into memory as a process, someone must make sure that some other process must not accidentally write something into my program area, must not destroy or disturb my space in memory where my process is loaded, right. Such things must be ensured. So, the different protection mechanisms that are typically supported by the operating system are, of course, the first one I have already just now mentioned, controlling access to files and directories by using the protection mechanisms. And of course, in most systems, particularly in Unix or Linux system, without a username and password you cannot get into the system, but in Windows you can also have, but you can also remove that if you want, but it is always a good practice to have a password based access to the system. So, anyone cannot access your system. If you have a valid login and password, only then you will be able to enter into the system. And as I said, the data of one user should not be tampered by some other user. This is the third important thing. One user should not be able to access the data of another user. Similarly, one process cannot change the memory area of another process, as I told just now. And as I mentioned in the last class, that the operating system consists of broadly two parts. One is the kernel, other is the shell. In the kernel, the main utilities or functions of the operating systems are there. So, when a user program is running, either accidentally or deliberately, I should not be able to tamper with the data or any code inside the kernel. That should be very secure. A user must not be able to do anything to the kernel code or kernel data. Okay. Now, to maintain this kind of security mechanism, some kind of support from the processor or the hardware is required. This we shall see slowly as we proceed through this class, that what kind of hardware support is required. But most important thing that is essential is that there is something called multiple mode of operation of the CPU. This we shall be explaining very shortly. Most of the modern processor has more than 2 modes of operation, but minimum 2 modes of operations are required to enforce this kind of security. So, this kind of 2 modes, sometimes referred to as dual mode of operation, is essential. Without that, you really cannot implement an operating system with adequate security mechanisms. Okay? Let us see what is dual mode of operation. Normally, what a processor does, CPU, it fetches some instructions from memory, executes it, again fetches an instruction from memory, executes it, and this goes on. Okay? Fetch, execute, fetch, execute, fetch, execute. But what we are saying here is that this much is fine. Fetching and executing are the most important functionalities of the processor. But the processor or the CPU will be having, let us say, 2 modes of operation. We are calling them user mode and the supervisory mode. The supervisory mode is sometimes also referred to as the kernel mode. Okay. Now, how do the processor know that which mode I am in now? So, inside the CPU, suppose this is your CPU, inside the CPU there is a special flag bit called mode, let us call it M. There is a special flag bit, this M is nothing but the mode bit. It indicates whether it is in the user mode or it is in the kernel mode. Let us say if it is 1, it is user mode, if it is 0, it is kernel mode. Okay. So, the CPU, just by looking at that bit M bit, will know that whether now I am in the user mode or in the supervisory mode. There is a little difference in the way it functions, we will just tell you. And the convention, as I said, when a normal user program is running, the mode of the processor must be in the user mode. When the user program is running, so the mode must be user, let us say the M bit is 1, M bit 1 means user mode. But when the operating system is running, usually operating system, whatever it does, it is very something critical thing, it is allocating memory, it is setting a lock, it is unlocking something. Those things the user program should not be able to do directly. So, whenever the OS is doing such things, the mode of the processor must be in the kernel mode or the supervisor mode. Let us say mode bit is 0. So, in the user mode, I am saying it is a normal mode, the user programs are running, but whenever something special is being done, let us say by the operating system, my mode must be in the kernel mode. Okay. Let us understand the difference between two modes. The main difference is that if you look at the instruction set of a processor, every CPU has an instruction set, right? You look at the instruction set. This is the instruction set of your processor. What we are saying is that the instruction set we are dividing into 2 classes. the first class we say that these are non-privileged instructions, and the other class we say these are privileged instructions. Non-privileged means anyone can use or execute those instructions. When some program is running in the user mode, you are allowed to run the non-privileged instructions, but the privileged instructions can be run only when the processor is in the kernel mode. In the user mode, you cannot execute a privileged instruction. What will happen if you try to do that? An exception will be generated, an interrupt will be automatically generated, and the operating system will be informed that the user program is trying to execute a privileged instruction, which it is not allowed to do. Okay. There are few instructions which only the operating system is supposed to execute, and user programs are not supposed to execute those. Those are put in the privileged class, those are the privileged instructions, right. In the user mode, you can execute only non-privileged instructions, but in the kernel mode you can execute anything, non-privileged or privileged. This is the basic difference. Now, how do the mode of the processor changes? The mode of the processor can change like this. Suppose the user mode, some program is running in the user mode, you want to change it to the kernel mode. The user program cannot change it directly. The only way it can change it is by executing a system call or trap. System call or trap, I told you, it is a special kind of a function call instruction, special type. It is used only when the user program is trying to call some functionality of the kernel. Okay. So, whenever such a system call is done, the mode changes to the kernel mode and the corresponding kernel routine starts executing. So, whenever the kernel routine is executing, the mode has already changed to kernel mode. Okay. Moreover, any kind of interrupt when it comes, timer interrupt, IO input output interrupt, that also changes the mode to kernel, because whenever interrupt comes, some interrupt service routine has to be executed, which is part of the operating system. But after this interrupt processing or the operating system, when you return back to the user program, then the CPU mode is sent back to the user. So, return from interrupt or return from kernel, there is a special instruction like that. When you execute that, the mode returns back to the user. So, I said, to summarize, user programs will always run in the user mode, and whenever it requires some operating system service or function, it will invoke a system call. All operating system functions will execute in the kernel mode. Okay. This is how it works. Now, to repeat this thing once more, a system call, essentially the meaning is that any program that is running can request some service from the operating system by invoking a system call. This is a very important concept, that is why I am repeating it once more. And you can pass some parameters to the function call. That parameter will indicate what kind of function you want. Do you want to operating system to allocate more memory, or do you want to set a lock, do you want to open a file, or something like that, what you want. And whenever you make a system call, control will transfer to the OS, the kernel routine will execute and control will return back. So, there are many such operating system functions you can ask for, many more are there, you shall see these things. Okay. Now, basically essentially what I am saying is that whenever diagrammatically I am showing you once, a user program is running, user program when it is running, the mode bit is 1, that means it is in the user mode, and whenever it wants some service from the operating system, it invokes a system call. When it invokes a system call, the mode bit becomes equal to 0. You go to a kernel routine, some kernel routine gets executed, and after that you return back. When you return back, a special return instruction will be used, so that the mode bit will again set to 1, and your user program got interrupted in between, it resumes execution again. This thing basically happens, and diagrammatically I am showing it here, the same thing what I showed. The user program was running, mode bit was 1, the user program makes a system call, mode bit becomes 0, and some kernel routine gets executed. After it is finished, it executes a instruction, special instruction to return from system call. That return from system call will set the mode bit to 1, and the user program again resumes. Basically, this is what happens, and this is a very important concept in operating system. Any operating system function is called through system calls. Operating system is not executing by itself, it is event driven. Whenever a user program requires a service, it will make a system call. Whenever a timer interrupt occurs, operating system some function will wake up. Whenever an input output interrupt comes, some operating system device driver routine will start executing. So, this is a very important concept you need to understand and remember. Various important functionalities of the operating system and some details about those. Now, in the subsequent classes, what we shall see is that each of these modules we have talked about, we shall be looking into further details, what are the other nitty-gritties and other details about those modules, what are the features and what are the other operating system functionalities that can be integrated into those modules to make them more usable and more functional. Thank you.